Chapter 12 General Properties of Wave.
This video is brought to you by Ace with Dennis. Now, learning can be smart, not hard. Don't forget to subscribe and press the bell notification button to stop missing out free lessons from me.
Waves transfer energy through vibration or oscillation. Energy is transferred in the direction of wave motion. However, waves do not transfer the matter. There are two types of waves: transverse waves or longitudinal waves. Transverse waves. Transverse waves are waves with vibrations perpendicular to the direction of travel of the waves. Let's imagine you hold one end of the string and another end of the string is attached to the wall. So you move up your hand and down your hand a few times. You produce a transverse wave. You continue to move down and move up, move down your hands, and you see that you are producing a series of transverse waves. The movement of your hand up and down shows the movement of particles which is perpendicular to the direction of motion of the wave, which is traveling from the left to the right. Let's see this diagram. This is the central position, and this is the direction of wave motion. And we mark a few points on this wave: point P, point Q, point R, S, T, U, V, W, and X. Now, how to identify the direction of motion of particles P, Q, R, S, T, U, V, W, and X? To do this, you can duplicate the wave for the next moment. This red wave indicates the wave of the next moment. You can extend the wave at this point to determine the movement for particle P. So, for this case, particle P moves downwards. Similarly, particle Q also moves downwards, same as R. For particle S, T, U, and V, they move upwards. For particle W and X, they move downwards. Hence, particles that move down are P, Q, R, W, and X. Particles that move up are S, T, U, and V. A particle on a transverse wave does not move with the wave. It moves up and down from a central position. Longitudinal waves. Longitudinal waves are waves with vibrations parallel to the direction of travel of the waves. Now let's talk about how to produce longitudinal waves. Imagine you hold one end of spring and another end of spring is attached to a wall. So you stretch the spring, and then move to the right several times, and you will see that you're producing a series of compression and rarefaction and compression. So we know that longitudinal waves are a series of compression and rarefaction. Now, how can we draw the waveform from longitudinal waves? What we can do is we take the center for compression and the center for rarefaction. For the center of compression, we mark it as the maximum point of the wave. For the center of rarefaction, we mark it at the minimum point of the wave. Then we join those points together, we can produce the waveform of longitudinal waves. So the peak of the wave is called the crest, and the minimum point of the wave is called trough. This is the crest, and this is trough. Sometimes longitudinal waves can be represented by the current state of particles. In this diagram, the vertical dotted line is the neutral position for the particle. Let's say this particle is at its neutral position. So it is moving to the left. You continue moving to the left until it reaches the leftmost position. When it is at this position, you will change direction and move to the right. You continue to move to the right, reaches the neutral position, and continue to move to the right until it reaches the rightmost position. When it is at rightmost position, it will change direction and start to move to the left, continue to move to the left until it reaches the neutral position. And it still continue to move to the left until it reaches the leftmost position and change direction again to move to the right, reaches to the neutral position, and the process repeats. Now, we can plot the waveform from this diagram. What we can do is, we'll take the neutral position and mark it at 0. For the leftmost position, we take its neutral position and mark it as the maximum point. For the rightmost position, we take the neutral position and mark as the minimum point. Then we join these points to form the waveform. And this distance is the amplitude of the wave. We can also measure this distance as the amplitude. Similarly, this distance is the amplitude. Now, let's learn some basic terms in waves. First, we need to look at displacement distance graph. So this is the displacement distance graph with its waveform. The first term that we need to learn is amplitude. Amplitude is the maximum displacement from rest or central position. Therefore, from this graph, this length is the amplitude where we measure from the central position to the peak. Or, this length is also amplitude as we measure from the central position to the maximum displacement at the bottom. Similarly, this length also amplitude, and this length is also amplitude. Next, wavelength lambda is the distance between any two consecutive points that are in phase. The SI unit is meter m. So from the graph, we need to identify two consecutive points that are in phase. So from this graph, we can see there are three pairs of two consecutive points that are in phase. The first one is the peak to peak. So this distance is the wavelength. The second pair of two consecutive points that are in phase is the trough to trough, and this distance is the wavelength as well. The third pair of two consecutive points that are in phase is from the origin to another 0 degrees here. So from this point to this point, this is also the wavelength. Next, let's look at displacement time graph. This is displacement time graph with the waveform. From this graph, we can identify the amplitude with this length. And also, we want to talk about the basic terms of period T. Period T is the amount of time taken for one complete cycle. The SI unit is second s. So from the graph, the peak point to another peak point is the period t. We also can measure from the point at this throw to the point at this throw as the period t. Or we can measure from the origin to this point as the period t as well. The next term that we need to understand is frequency f. Frequency f is the number of complete cycles per unit time, which is in second. The SI unit for frequency is hertz. F equals to 1 over t. So this is the formula for frequency. Next, the speed of wave v. The speed of wave v is the distance traveled by wave per unit time. Therefore, the formula will be v equals to distance traveled in one period over the period. So v equals to wavelength lambda over t. We can rearrange the formula and we'll get v equals to f lambda. So this is a very important formula for wave. Now, let's discuss one important experiment which is called Ripple tank experiment. We conduct this experiment to study wave in the lab. So this is the setup of Ripple tank experiment. First, this is the Ripple tank, which is made of transparent glass. It is filled with water, and we place the dipper at this position. This dipper is connected to a motor, which will vibrate at frequency of 50 Hz. When it vibrates, a series of ripples will be produced and move at this direction. We place a piece of white paper at the bottom and shine a lamp from the top so that we can see ripple shadow on the white paper. If the dipper is in spherical shape and it moves up and down, it will produce circular ripples. If you observe these circular ripples from the top, this is what you can see. The solid lines represents the crest, and the dotted lines, which is invisible, are the throws. The distance between the crest to crest is the wavelength lambda. So, if we take this cross-section, we can plot the displacement distance graph with the waveform. So, if this is point A, this will be point A, and if this is point B, this will be point B. If this is point C, this will be point C, and if this point D, this will be the point D. The distance between point A to point D will be the wavelength lambda. Similarly, B to C is lambda, C to D is lambda as well. Crest also represents wavefront. What is wavefront? Wavefront is imaginary line connecting points that are in the same phase. So if we see this waveform as a three-dimensional shape, and we observe from the top, these lines are wavefronts. If the dipper is a straight dipper and moves up and down, it will produce this series of ripples. And if you watch from the top, you will see this series of wavefronts. The distance between the crest to crest are the wavelength lambda. In ripple tank, frequency of the wave is dependent on the wave source, which is the oscillation of the motor. Usually, it is a constant. Hence, from the formula v equals to f lambda, the speed of wave is dependent on wavelength. In river tank, the depth of water affects the speed of wave. Hence, wavelength will be affected as well. The deeper the water, the less resistance the wave will experience. Hence, the wave can travel faster or at higher speed. We can observe that wavelength increases as well. On the other hand, the wave experiences greater resistance in shallower water. Hence, the wave travels slower or at lower speed. We can observe that wavelength decreases as well. So this diagram illustrates how we can change the depth of water in river tank by just placing a glass block. So this is the direction of wave, and we can observe that this is the deep water, and this is the shallow water, and this is the deep water. So at the deep water, we get larger wavelength. At the shallower water, we can see smaller wavelength. And in the deep water, we can see larger wavelength again. So if we view from the top, we can see this series of ripple with the direction of wave is this direction. So from this region, this is the deep water. This region, this is the shallow water, and this region is the deep water. Now, let's talk about the refraction of wave in ripple tank. Let's say this is a glass block, and the ripple enter the glass block at certain angle. So this is the deep water, and this is the shallow water. First, we draw the normal line, which is perpendicular to the borders. Then, the ripple will bend towards the normal when it travels from deep water to shallow water. So, at the shallow water, we'll draw the ripple with shorter wavelength. Then we complete the diagram with the wave at the borders. Then, we know that I and R here is I is the incident angle and R is the refracted angle. Wave bends towards normal when travel from deep region to shallow region. This is because the speed of wave decreases when entering shallower water. Therefore, I is greater than R. Now, how about when the ripple entering the deep water again? So, we are doing the same process. First, we draw the normal, which is perpendicular at the border, and the ripple will bend away from the normal. Then we draw the ripple with larger wavelength at the deep water region and complete the diagram with the wave near the border. So this will be our incident angle and this will be our refracted angle. Wave bends away from normal when travel from shallow region to deep region. This is because the speed of wave increases when entering deep water. Therefore, I will be less than R.
That's all for this video. Thanks for watching. Do you have any question or doubts to ask? Feel free to write down in the comments. I would love to hear from you. Do you like this video? Please don't forget to like it and share it. Alternatively, you can also enroll this full revision course at Udemy. At Udemy, you can track your learning more effectively. Download my notes in printable PDF form. Take a summative quiz at the end of each chapter. Get your first-hand updated contents from me. Get quicker response from me, and many more. You can get all these benefits at a very affordable price. It is one-time payment, no recurring fees, no hidden costs. This saves you thousands of dollars on expensive tuition fees and revision crash courses, and most importantly, your precious time. Finally, you can do your revision anytime you like, anywhere you prefer. All is available within your fingertips. Check out the description below this video and click on the enrollment link to register the course at discounted price. Alright, until then, see you in the next video. Have a great day ahead.